I want to welcome you to the monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information and resources for renewable energy and energy systems integration decisions. We also provide peer-to-peer networking opportunities, information and knowledge sharing, and professional education experiences. Our most recent activity was our fall technical workshop in Charlotte in October. And our next activity will be the spring technical workshop in Tucson in March. That'll be followed by our International Energy Systems Integration Workshop with the Australian Electricity Market Operator, AEMO, in Australia in April. There's still plenty of time for making plans to attend any of these, so please feel free to do so. These workshops deal with a full range of issues associated with integrating wind and solar into electric, gas, and thermal systems. They also deal with a coupling to energy-consuming infrastructures, especially electric transportation, buildings, and industry. Information is available on the website on the upcoming workshop schedule for the next year, and all are welcome. ESIG is a very unique organization, and I don't think you'll find anything quite like it anywhere else in the world. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. So please use the question and answer box on the lower right side of your screen, not the chat box, to submit questions. And we'll try to save 10 minutes or so at the end for the Q&A. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the presentation and the audio file have been posted. We also plan to provide short responses to unanswered questions after the webinar, so don't be afraid to use the Q&A box. Okay, so today the webinar is on the topic of converter-based generation model development and validation. Based on the registrations, it looks like this is a very popular topic. The webinar will feature Ryan Quint, a Senior Engineering Manager at NERC, and Bob Zavadil, Chief Operating Officer for the consulting firm EnerNex, the CESI company. This webinar is actually an update on a similar one that Ryan and Bob gave a year ago, which was also quite timely and quite well attended. Ryan, in his role at NERC, coordinates a number of NERC technical groups focused on emerging risks, grid stability, converter-based resources, and modeling improvements. Ryan's an active participant on Joint Working Group 5 of the IEC SC8A. The IEC is an international standards development body for a broad range of electrical and electronic industrial equipment sold in global markets. SC8A is a subcommittee dealing with grid integration of renewable energy generation, and JWG5 deals with issues regarding control system interaction and grid stability. I have to say that Ryan's becoming an internationally recognized expert in this area. Bob is a well-known expert in electric power system issues for wind power plants in particular. He supervised many wind integration and interconnection studies in both power systems, and he's worked with everyone from wind turbine designers and manufacturers to project developers and operators, to transmission service providers and independent system operators. Bob has over 35 years of experience in the industry, and he chaired our modeling and interconnection working group for many years. He's a regular participant in ESIG meetings. I feel very fortunate to have Bob and Ryan here with us today. And on a personal note, as I've gotten in the habit of doing, I took a look on LinkedIn last night. Now, this is particularly interesting to me right now because I did the same thing a year ago when Bob and Ryan did a similar webinar. I found out that Bob and I still have only 3 shared connections, and my shared connections with Ryan have grown from 129 to 161. Since Bob is a long-standing friend of 30 years, I can only conclude that he's not very active on LinkedIn. But make no mistake about it, he's certainly very social.
Thank you very little, Charlie.
And since I've only known Ryan for around 5 years, I guess that means he's increasingly active on LinkedIn and also quite social as well. Anyway, I consider them both good friends, and it's a pleasure working with both of them. The purpose of the webinar today is to familiarize key industry players with the latest industry efforts focusing on modeling and model validation activities for bulk power system connected inverter-based resources. We'd also like to touch on some new developments regarding modeling of grid-forming inverters, which are a hot topic in R&D circles, as well as some current power system applications. So, okay, without any further ado, let's go ahead and get started. And Ryan, I'll turn it over to you.
Great. Thanks, Charlie. Thank you for the very kind introduction. I'm very honored to be back again and talking about this topic again with Bob. I think even now it's more timely than a year ago and more timely than ever before to really talk about these topics of modeling and verification, parameterization of these models, et cetera. So what I'm going to focus on is it may not be the most popular topic, but I'm glad to see that the attendee list continues to grow because this is more important now than ever, like I mentioned. So it may not be popular, but it's grounded in fact. And so I encourage everyone to take the things that I'm going to talk about here today very seriously. And as we get into it, I think you'll see why. So the upfront disclaimer here, this is not intended for compliance purposes. While I work at NERC, I work on the reliability side of the house, and my goal is to support the industry and improve reliability and address these emerging issues. These are based on my experience and engagement with the industry stakeholders and may not be the opinions of NERC itself. And if you have any questions related to compliance, feel free to share those with our compliance assurance department, and they'll likely loop back to myself and others for technical guidance. So I want to start with the big picture, the 50,000 foot level above where the planes fly. The grid itself is changing rapidly, more rapidly than ever before. We're seeing interconnection requests. The time between interconnection request and in-service operation has shortened more than ever before, and plants are coming online so fast, particularly solar, energy storage, et cetera, that they don't even sometimes get into our assessments at the NERC level because of how quickly they're interconnected, and I'll talk more about that. But it's our responsibility as stewards of reliability to adapt to these changes and ultimately ensure reliable operation of the system moving forward. And so we need to be looking ahead at what's coming down the pipeline and how do we address those issues in this kind of rapidly evolving environment. And I feel like we're sort of handling that long time inertial aspect of our industry and all trying to overcome that to move quicker than we ever have before. And so I encourage everyone to get involved. And a lot of the folks on here, I'm very familiar with a lot of the names, which is great to see everyone, participating in all the forums that we can. So we at NERC have been very busy on these topics of inverter-based resources and performance, particularly on the solar PV events. And so hopefully everyone's familiar with these disturbance reports and NERC alerts that have come out over the past few years, going all the way back to the Blue Cup fire from August 16, 2016. And even more recently, we published a report early this year on the April and May 2018 disturbances that happened in all these in the California area. We sort of analyzed them and developed best practices. So there's a lot of material out there that is sort of leading the industry towards recommending changes and collecting data. And I'm going to talk a lot about what data we've collected and what the findings are from that data collection. All of that work led to these two guidelines that came out of the NERC IRPTF. The first one focusing on bulk power system connected inverter-based resource performance. So how do we want these resources to behave? What is the recommended performance for newly interconnecting resources and even existing resources to the extent possible? There is not a lot of clear guidance in North America on how resources should behave when they're connected to the grid. And so the goal of that initial guideline was to provide that guidance. That sort of served as the foundation and the initiator for P2800, which is doing a tremendous job on trying to standardize that performance looking forward. And we tried to get a handle on that as a start with that guideline to sort of set the stage for that. So more recently, in September 2019, we published the next guideline, which was really a cookbook on how do we improve the interconnection requirements on the transmission entity side, the transmission service providers, for these newly interconnecting resources for bulk system connected inverter-based resources. When you look at the interconnection requirements, a lot of them are not unclear or not concise on how to handle inverter-based resources. So while we're not trying to develop additional requirements or go above what the existing fleet has, we are trying to set the stage with clear, concise guidance and requirements on how these things should be interconnecting in terms of performance, models, et cetera. I'm going to dig into that as well. So let's start with some of the data that came out of the NERC alert following the Canyon 2 fire disturbance. SCE, under the umbrella of the California ISO, the CAISO has been really working on developing a massive amount of modeling improvements. So coming out of the Canyon 2 fire disturbance, we saw very clear data that there was lack of modeling information, lack of model accuracy, particularly with the models that are submitted for the interconnection-wide base cases. So CAISO, in response to that, has embarked on the multi-year process to update these models, and I'll dig into that here shortly. But just as an example, let's go through the Southern California Edison modeling improvements, and they provided this update back in September 2019 at a NERC meeting. So of the 3,700 megawatts that are BES, bulk electric system resources under the jurisdiction of NERC being BES resources, they sent out the initial phase 1 data request to 2,400 megawatts. So 2,400 megawatts of capacity. That the request went out to those GOs. At that time, 1,900 megawatts had responded to the NERC alert or to the follow-up, and 565 megawatts hadn't. Of the 1,900 megawatts, 1,867 of those megawatts use or employ momentary cessation as their large disturbance ride-through form. 61 megawatts are using some other type of ride-through like reactive current injection or something. So CAISO, SCE, reviewed those models that were provided based on the request that went out, and of the 1,867 megawatts of capacity of resources that provided models back, every single one of them was deficient. And so while you see these phase 1 findings here, let's really go to the important findings. 0% of the models that employ momentary cessation were considered acceptable by the transmission planner and the planning coordinator. And 98% of the solar PV capacity have models that with uncertain quality or accuracy. And what I'm saying there is, while the model may or may not be correct, at this time, we have identified deficiency or uncertainty in the quality of those models in 98% of them. And I'm giving credit to the 61 megawatts that don't use momentary cessation and making an assumption that those are correct, even though those were not part of this analysis and therefore also are kind of uncertain in terms of the quality. So like I said, this is a multi-year process, and this is PG&E's timeline under the CAISO process for what's in their footprint, and that red line has shifted a little bit since over the last 3 months, but you get the idea. This is a 6-phase process over multiple years. So until the end or middle to end of 2021, we have models out there that have not been, not been analyzed, not been reviewed, and we are not sure of the quality. And like I mentioned above, when the phase 1 requests went out to get updated dynamic models that accurately represent reality, that request went out. They send back the models. The TPPC identified deficiencies with those models, and then they call them cures or corrections need to be made to those models. And they're sort of in the midst of that phase 1 deficiency process review, and then they'll be going into phase 2, phase 3, et cetera. So like I said, multi-year process, and a lot of work is going into trying to get these models updated for the existing fleet. So what were the predominant issues? I'm going to skim through this pretty quickly, but the materials provided here, you can come back and look at it later. So models were failing the basic quality checks that we're all used to. Incorrect data formats, the model doesn't initialize, it doesn't provide a flat run, it doesn't exhibit any positive damping, or it goes unstable for a normally cleared fault, et cetera, et cetera. Those are the types of basic model checks that we're used to. The 2 bigger issues that we saw was a mismatch or an incorrect parameterization of these models. So the biggest one was a mismatch between the model and the actual installed settings. So many of the resources use the RECA model, which has the capability to model momentary cessation, but the data provided in that model didn't match the NERC alert data. So while the GEO said I use momentary cessation and I have a half a second time delay and I have a 30% per second ramp rate, the RECA model was set up to provide reactive current injection. So you can quickly do a cursory review of the model and the data and realize these don't match. That's not a correct representation. Another big issue was that many of the models are using the RECB model, yet they're employing momentary cessation. And as we've discovered in IRPTF, RECB really doesn't do a well enough job or good enough job of capturing the characteristics of momentary cessation, including the ramp rate, the time delay, et cetera, to be able to capture momentary cessation in the level of detail needed for local reliability assessments. We really need the REECA model in those cases, and in a lot of cases, the REECB model was provided and it doesn't capture momentary cessation. The WEC has published a white paper on how to convert those models. However, it doesn't appear that those recommendations are being taken seriously or being applied by the industry because the models that were provided during this process were REECB. So additional issues, suspect data, suspicious data, default parameters that are used in 20, 30, 40 identical parameters for different plants across the interconnection. That looks suspicious. Often that they're the same values that come straight out of the software manuals. So the PSLF, PSSC manuals have default values and they're likely using those. And it's very unlikely that every single parameter value for the plant level controller and the equivalent representation of the inverters matches in those many cases. It's kind of questionable and needs to be validated. We heard back from TPs and PCs that there's uncoordinated parameter values between the voltage dependent current logic table, the VDIP parameters, and the current prioritization for the large disturbance. It's a really complex topic, and it often requires experts to really get those parameters right and tune them and make changes to those models. It's not an easy task, and that's likely part of the problem there. And we've heard anecdotal evidence, which is a little scary, that multiple plants have made changes to the control settings in the plant controller, the inverter settings, et cetera, without providing an updated dynamic model to the transmission planner or the planning coordinator. They're just making changes and the models are not following suit. Really, it should be the other way around, that an updated model is provided, it's studied to ensure reliability, approved by the transmission service provider, and then the change is made by the generator owner. But that's not what's happening right now. And GOPs have stated that they didn't consider that a material modification when they swapped out the inverter settings or the plant level controller settings and they changed operating modes, and therefore they didn't provide any model to the planner prior to making those changes. They just made the changes without prior approval. There's a lack of information available to the transmission planners and the planning coordinators to verify whether the dynamic models are accurate. There's a lack of data in the Mod 26 and 27 test reports, and I'll talk about that. There's an unknown type of data provided during the interconnection process. It's really not clear what needs to be provided. And the NERC alert was really the first time that we went out and said, give us actual installed equipment settings so we, as the transmission side, can go verify that the model matches reality. Before that, we've been sort of running blind with lack of data on what's actually out there, not just a model that is supposed to reflect what's out there. We've also heard that a lot of the transmission entities are under a serious time crunch to run the necessary studies to be able to ensure reliability, and it appears that there's a lot of corners being cut, and really they're on the modeling and the model verification and the model accuracy checks and things like that. And receiving an updated model after the interconnection process is nearly impossible and definitely not a recommended approach. So lastly, the studies with up-to-date models for both BPS-connected inverter-based resources and distributed energy resources are not widely being performed. So while the IRPTF studies are using extremely accurate, most up-to-date bulk system inverter-based resource models, DER was not the main focus and wasn't really considered in those studies. Similarly, when we're looking at wide area DER studies of implying, say, the DERA model, those are spending a lot of time focusing in on the DER models, but they're using the interconnection-wide base case bulk system inverter-based resource models, which we know have systemic modeling problems, and you could essentially call them inaccurate models for the bulk system, particularly the solar PV resources. So there's really no studies out there that at least we're aware of that are bringing all of this together and updating all of the models and getting these accurate in the future-looking studies. EMT models are often not provided during the interconnection study process. They're extremely difficult to get after the fact, after the in-service date, and especially if there's, say, a manufacturer that goes out of business or something like that, then those models are nearly impossible to collect. And so there's challenges with the rapidly evolving technology, because without those models, the planners are having to make big assumptions on how these things behave, and that's presenting challenges to certain grids. And we know that there's limitations in the positive sequence simulation models, the RMS tools that we typically use for dynamic simulations, inability to capture some stability type issues, particularly under high penetration conditions, controls interactions, control cycling, controlled instability, SSCI, low short circuit type grids. Those models have limitations. And it's often the fact that EMT simulations are not commonly performed during the annual planning process, and we may miss things. I'll talk a little bit more about that. So there's a long timeline from interconnection request all the way down to in-service operation and the Mod 33 type system level model verification, where models come into play here in terms of the feasibility study, system impact study, annual planning assessments, annual Mod 32 case creation, the Mod 26, 27 verification. All of this centers around modeling, but there's really nothing in here that says I got to actually provide an accurate model. There are capabilities in some of these requirements and standards and activities that could enable improvements to models, but nothing really in here that says you have to provide an updated model that accurately represents what's out there and have that be a truly verified model. So let's start at the beginning, at the interconnection request. So I just pulled up the LGIA, attachment A to Appendix 1 of the LGIA. And if you look at the synchronous resources, there's a whole bunch of material in there on what needs to be provided there on the left. You can see inertia constants, reactance values, time constants, power factor, all these things, and they're even making a nod to minimum and maximum state of charge for battery or energy storage resources. But then look at the top right there for wind resources. What they're asking is the number of generators, the elevation of each of those generators, the manufacturer model, serial number, etc., and then a list of adjustable set points. And it does make a nod to having a PSLF or PSSD power flow model and the associated dynamics models, etc. But really it's kind of vague. And it says all of that will be discussed at the scoping meeting. And when you look at what's in there for solar, it's blank. There's nothing in there that mentions a solar PV resource. So what do we provide? When you look at it for synchronous machine, it actually states, which is really great, it states you got to provide, capability curves and V curves and saturation curves and all of these things that a planner or a transmission entity could look at and verify that the model matches what those curves say it matches, says it should be. But when you look at a solar resource, you really can't do that. You're going to receive a model, and it's unclear if you're going to get an inverter spec sheet and a plant level controller spec sheet and a picture of what the nameplate of the transformer looks like and a picture of what the inverter settings are, etc. With that information, you could do quite a bit of verification and say, well, does this model actually represent what's actually installed out there in the field? So to further complicate it a little bit, let's look at the FACT 2 standard, the NERC FACT 2 standard, which says each TP and PC must study the reliability impacts for newly interconnecting resources and materially modifying existing resources. And 1.3 down there says steady state, short circuit, and dynamic studies as necessary to evaluate system performance. Now, I could go out on a limb here a little bit and say, well, technically it says dynamic studies, it's not really defined, and so maybe EMT does land in that bucket. That a sufficient amount as necessary, EMT studies need to be performed for newly interconnecting resources and material modifications, but that's really not all that clear, because dynamics to most people means the RMS positive sequence studies that have been performed for many, many years now, and likely it doesn't it doesn't make us think about the EMT studies that likely are needed in the future. But the confusing part is down there at the bottom where it says, well, what is material modification? And it's essentially saying that each entity needs to define what material modification is, and that should be based on an engineering judgment assessment, particularly for the FACT 2 standard, right? We're not talking about the FERC process. This is a NERC reliability standard for interconnection studies. So let's go look at the FERC definition. So there's actually a definition of material modification in the FERC process, and likely there's a bit of confusion here, and we've heard this from multiple industry members. In the FERC realm, material modification refers to a modification that has a material impact on the cost or timing of an interconnection request with a later queue priority position. And it talks about permissible technological advancements that need to be defined by the transmission provider. But really it's looking at, do I have an impact for where I am in the queue as a generator to queue requests that are below me? And if I'm going to make a change that impacts people later on in the process, then I'm considered a material modification and I got to go back in line. It's not really looking at, do I have an impact to the bulk power system performance or the change in performance of how the system behaves based on the way that I operate? And I think ultimately there's a lot of confusion about what material modification means in Fact 2 and the LGIA, LGIP, and SGIP process. And these are not intended to be the same thing. So wouldn't you want to restudy the potential impacts of changes to facilities if they have changes, if they'll affect the electrical performance of the local system? So changes to the inverter type or the size or the control settings, the plant level controllers, the dynamic reactive support, are those considered material modifications? Well, it's unclear whether or not they have an impact to the queue request later on in the process, but they of course will have an impact if they change the electrical performance. They're going to impact the bulk system and how it operates. And so I think most transmission entities would say, well, yeah, we need to study that and make sure that it's acceptable before those changes are made. But we've heard that that's not necessarily happening. So again, the Fact 1, Fact 2 standards are critical. We need to define interconnection requirements and make sure they're very clear. And then we need to make sure we're performing adequate amounts of studies for newly interconnecting resources and material modifications. So again, I recommend the guideline. Take a look at the guideline. It provides very strong recommendations on how to integrate these into your interconnection requirements per the Fact 1 process. And really, there's a big focus there on the models and updating the models. So once the resource is interconnected, a lot of people rely on the Mod 26 and 27 dynamic model verification activities, right? We've just gone through the 10-year cycle and most of the existing resources have been verified. But the challenge we have here is that you can meet those standards with small disturbance verification tests. So small bump tests and reactive set point value or cap switching tests or a change in the injected frequency signal into the plant level controller, and you can watch the plant behave and you can get a nice match of actual versus modeled performance. The challenge is that we don't capture any of the large disturbance behavior that would dominate the performance of the resource, like during a fault event. And so from my experience and what I would think would be the expectation for a verification report is really a thorough explanation of why were the models used, what models are selected and why, what values are entered into each of the parameter values for that model, and then what's the explanation of the derivation for that parameter value. And it doesn't have to be from a test that shows a match between actual versus model. These can be commissioning reports, verification reports, factory test reports, type testing, communications with the OEMs, or even just engineering judgment in many cases. But having some type of explanation of how these parameter values are derived is really kind of critical to making sure that those models are quote unquote verified. So do we have a gap with the large disturbance piece? Well, we have evolving technologies, evolving models, really no requirements for providing spec sheets or actual settings. We're only doing small disturbance tests. We're seeing lack of detail in the test reports, and we need a much more thorough review of the models and the parameterization of those models. So I'll leave it up to you to decide whether or not we have a gap. And the UK grid disturbance that just happened is a great example. And you look at the kind of controls instability, they kind of call it resonance. I'm going to call it controls instability here. But the plant essentially found itself operating in a state that kind of led to some controls instability. And again, a lot of this is speculation, but I'd be very curious on, were sufficient level of detail of studies performed to ensure reliable operation of this plant under all expected operating conditions, which likely would have required an EMT type simulation because of these higher frequency type of oscillations that occurred and buried in the detailed controls of that plant. Now, maybe the positive sequence models could have picked it up, maybe not, I don't know. And so there's a number of interacting things here, but this event really just highlights the need to get the models and the studies right. And I think that the UK grid, definitely has a good opportunity to learn and kind of, drive improved performance moving forward. And it's a great case study for the rest of the world to use to understand really what are the best practices and where do we go from here. So we're seeing a growing need for the EMT type simulations, the models, controls instability, control cycling, as you can see here, controls interactions. All these things often aren't picked up with the RMS positive sequence simulations. And so if you're not running these, you're not going to see them. And obviously that requires engineering judgment to determine when should we be running these types of studies, in what cases, how, all of that stuff. And in the RPTF at NERC, we're really kind of digging into that and trying to provide as much guidance as we can. In the latest guideline we published, we did talk about the need for having EMT model benchmarking, so a comparison of the RMS positive sequence tool and the EMT tool to make sure that those models match, because they really should. To some degree, we need to see a general match between the performance of these models so we have some justification or understanding that which model should be used in which case. Now, in a lot of cases, they won't match identically. The EMT model is capturing a lot of things that the positive sequence model likely isn't. But we need to at least have some verification that these are generally good models and they match each other. So again, I can't stress enough as I wrap up that the system's changing. We need to adapt to these changes. That requires changes to the modeling approaches and the study approaches. Otherwise, we're going to essentially find ourselves in unstudied operating states that we don't really have assurance on that they're in a reliable operating state. And so we have a lot of work moving forward to get updated, or to gain an understanding on how best to approach that extremely technical and challenging topic. So the one thing I can recommend is to get involved. We've been very busy at the NERC level and coordinating with WEC and all the operating entities across North America to really get a handle on this. And there's a lot of best practices going on. There's a lot of good things happening. So we have guidelines, disturbance reports, NERC alerts have gone out, a great summary there at the second to last bullet there that talks about the overall NERC activities that are underway. And again, all of this sort of lands in the P2800 world to really kind of standardize the performance, the models, a lot of this stuff for newly interconnecting resources in the future. But we can't wait until we have P2800. We need to be taking action now, because between now and when P2800 gets approved a couple of years down the road and enforced in some way, we're kind of running in a blind area that we need to better maneuver. So I guess with that, I'll just say thank you and hand it over to Bob, and then I think we'll have some questions at the end. And if you are interested in getting more involved or have any follow-up questions, feel free to shoot me an email, and we can continue the discussions then.
All right, Ryan, are you going to hand me the ball?
Sure.
There we go.
There you go.
Thank you, Ryan. A lot of stuff, a lot of progress since last December. Plenty of places for folks to jump in. I wanted to spend a few minutes at the end of this webinar talking about an emerging topic. Those of us that in and around this area have probably heard it, and it's the whole notion of the grid forming inverters relative to the state we're at, which is acknowledged to be in some sense grid following. And I've been thinking about this for a while, because I think the whole notion of grid forming in terms of, our perspective initially felt like something really new. And as I thought about it, I realized it wasn't that much different. And I wanted to put some thoughts on paper and throw it out there. A lot of you folks are maybe way past me on this, but I just wanted to provide a little perspective to see if we could move things along. So inverter-based resources is the major topic. We've been at this in terms of the modeling and technology for 15 years at least. We've progressed sort of through the second generation of generic models for the bulk system planning tools, the RMS positive sequence. As Ryan expressed, we're understanding that we may need EMT models to plug some gaps. However, some of the very earliest concepts are still with us, and one of those being the control concept, where we can, from IBR, independently control real and reactive power, especially in the steady state, but sometimes, the reactive current injection during faults, that sort of thing. But the whole idea is based on injecting currents into the grid. And I believe personally, being around for that long, that, early on when we looked at a 600 kilowatt wind turbine, we realized, well, the grid's going to be there, so we just really want to focus on getting the appropriate currents stuffed in the grid, not thinking about even the penetration levels we're at now, and the fact that some of these plants are hundreds of turbines, so kind of a different thought with regard to impacting the grid. So we didn't really think about the grid voltage other than we needed to track it so we could calculate these quadrature currents correctly. And we really didn't care about the grid frequency because we were following. Now, when we started to look at synthetic inertia and that sort of thing, we saw where we potentially wanted to relate the power output to the grid frequency. So we had to sort of pick it up in parallel as a separate control path to affect that behavior. Um, so I went back to thinking about the fundamental operation of voltage source converters, and really, in all cases, we're making a voltage on the immediate terminals of the power converter. So in this simple example, I have X could be the output filter, it could be the output filter plus the generator step-up transformer, whatever, but it's an X. And on the other side of the X, I have a grid voltage. So I'm making, in all cases, a voltage on the immediate terminals of the converter, but I may not really even be concerned about it. Okay, there's a couple of general ways to control the modulation or the switch state of each of the switches in the converter. So in a lot of cases, we have a pulse width modulated scheme where the carrier that we're overlaying is in fact that voltage. But there are others where it's really not part of the control. If I'm only looking at currents and I'm using, for example, the hysteresis current modulation, that VT really doesn't show up in my control at all. So the basic operation of grid following inverters is to make currents that are appropriately aligned with the grid voltage. Okay? And so that requires us to track the grid voltage in terms of phase and frequency, and that's generally done through the phase lock loop that I have shown here. Keep in mind, this is kind of a generic level of detail so that when we're talking positive sequence RMS, quarter cycle time step, we really don't even have that PLL loop. We are getting EG and the angle directly from the program. But in any case, we have desired outputs. We kind of know what's going on, and we make adjustments, but we're making the currents when we're following the grid. Now, if we take a step back, and this is stuff we all know, the fundamental equations for power control in AC systems, where we have two voltages, an intervening X, and that P and Q. I have those two equations shown there, P and Q, and the one thing that jumps out at me is I isn't part of them at all. Okay? And basically, VT, that corresponds to the previous diagram, is the V behind Z, which is the classic sort of source representation. So pretty straightforward. So if we step ahead and think about a very simple grid forming inverter, we can think in terms of those same control loops, but my primary control variable is VT, and VT there should be marked as a phasor because I'm talking about magnitude and an angle. And in this case, I have desired P and Q. I'm measuring what P and Q is at, and then I'm calculating some compensating voltage that I instruct the converter to make, which is VT. So how does this get synchronized to the grid? Another kind of interesting thought experiment. If I've got a converter, an IBR, and I've got a precise sort of 60 hertz timing, okay, without any current flow, I can make that VT. It would be 60 hertz at some initial magnitude. So if I want to connect to the grid, I do it the old-fashioned way. I look at delta V across that switch. And what I do is I adjust the speed or the frequency of my source and the magnitude so that the delta V is 0 under conditions of no current flow. I can then close the switch and then further adjust the magnitude and angle to essentially affect the output in terms of P and Q that I'm looking for. We can think farther on that in terms of if there's a disruption in EG and what happens, but the same fundamental sort of feedback still applies. So going one step further, if we think about the voltage, the grid forming inverter operated both connected to the grid and disconnected to the grid, the sequence is kind of like I show here. Initially, S1 is closed, S2 is open, and I'm already synchronized, so I'm transferring P and Q to the grid. I could close switch S2, okay, under which cases for that condition of the output, now all of a sudden, what's flowing across S1 is actually 0 because it's being consumed locally. So I could take a step further then and open S1, And basically, my local island will continue, and it'll be stable operation, okay? Because the converter is making VP, okay, that's demanded by the local load. If you think about a grid following sort of control, you can run for a while like this, but a slight perturbation would probably knock it down, okay? But in this situation with the grid forming inverter, it should be absolutely stable if everything is right. So just a quick summary, and there's a lot more to be said and is being said on this. The grid following and grid forming inverters are really close cousins, in my opinion, and it's a matter of sort of a control structure and strategy. Doesn't mean that you know, I need grid forming if I do need grid forming if I'm looking at supplying an island. Both grid forming and grid following could be used with a strong grid. There's a lot of research going on in this area, and thinking forward to high or very high IBR penetration is a lot of questions that need to be addressed. Because while I'm looking at the IBR, the grid forming as sort of a conventional source, I'm not bound by the physics in terms of how fast I can adjust the excitation or how fast I can adjust the speed. And so if we think about that, it's kind of wide open if you're talking about coordinating the operation of dozens or hundreds of these across the grid. Now, the one thing that kind of falls out of this for the near term that I think is interesting is there may be some positive benefits with regard to the modeling, and I'm talking about the bulk system analysis tool, because in those we don't have really a PLL. We know how the grid is lined up, so we get that by default. But as we go through the control loops, we end up commanding a current source to inject currents in the grid. And there's some speculation that multiple instances of those in a weak area of the grid may be contributing to the model convergence problems and that kind of stuff. And you know, I'm not a programmer. This is way above my pay grade, but there's speculation that that may be the case. So if we think about the grid forming structure, where we're essentially commanding a voltage magnitude and phase angle behind an impedance tie to the grid, that's a sort of a more conventional structure for sources, and B, that it may help to address some of the numerical stability challenges we're having. And then, of course, going forward, when we're talking about actual grid forming, you know, inverters everywhere kind of thing, it's where we need to end up anyway. So with that, I'll turn it back over for some questions. I just want to point out that Charlie has spearheaded Power and Energy Magazine special issue. What is this, the 8th or 9th one, Charlie? And recommend that everybody pick up a copy or read through the copy because it provides a good update globally on where we're at with regard to this stuff. So thank you very much, and I think we have time for questions.
Okay, thank you, Bob, and thank you, Ryan. I think we've got some time left for questions. I don't see any questions in the Q&A box, but I want to remind everyone that the lower right-hand corner of the screen is the Q&A box, and feel free to submit questions. So let me begin with a question for Ryan. Really has to do with the availability, timing and availability of validated models for the inverter-based resources. I guess my recollection was a few years ago, Ryan, that NERC was moving very firmly in the direction of making that a requirement for interconnection before the, at least before the breaker was closed and the unit was operating. So what happened to that, or where do we stand with that, or how are we still getting unvalidated models getting into transmission operators' hands?
Yeah, it's a good question, Charlie. So I think we've been kind of looking at this in the IRPTF. So, you know, in terms of the history, I'm not sure how much I can provide there. But, you know, when I look at the FAC 1 and FAC 2 standards that I mentioned, I think they sort of implicitly state what you just mentioned, that, you know, the interconnection requirements should be robust, clear, concise, enough that you're going to get the data you need upon interconnection And so having a clear set of requirements is necessary, and it's ultimately up to the or the TO, I guess, really the transmission service provider, to provide or to specify those. And then it's up to the entities, whether it's a generator owner, or, line load, et cetera, to meet those requirements prior to interconnection. But if those requirements aren't clear, then it's kind of easier to meet those requirements with things slipping through the cracks. And I think the same thing goes for the study process. I think historically, looking back even say 5 years ago, I think the power flow, short circuit dynamics, RMS positive sequence studies were sort of intended to be sufficient. But as we see kind of these more and more low short circuit strength networks, high penetration grid conditions, we're seeing all these newer types of problems that don't necessarily show up in those studies. But it kind of, like you said, it comes back to, well, how do we know that those models are actually accurate and representative? And that's why we've been kind of working with FERC staff and talking about this in the IRPTF quite a bit, and trying to put some of this, some of these observations in an upcoming report out of IRPTF focused on modeling that kind of talk about, well, when you look at that interconnection request and the process from the very beginning, it doesn't really clearly state what's required to be provided for the purposes of modeling during the interconnection process. And so if you just provide a model, transmission planners have said, well, I've got to take that at face value. I run my studies, everything looks fine, and I hit the acceptable button, right? There's not much in there that says, well, you provided me a model, prove to me that that model is actually correct. Provide me with plant level controller settings and inverter level control settings and things like that, where you could do some validation or some verification of the model matching the expectation of reality. It doesn't necessarily have to be an actual test. So I think a lot of it comes back to the very initial interconnection request and the data that's provided then, and also what I mentioned on the mod 26 and 27. There's oftentimes the response I get when we say we have model challenges is we haven't worked through the mod 26 and 27 process yet. Well, we've learned through one iteration of the mod 26 and 27 process that you can meet that standard and have an entirely incorrect model. And that's been at kind of the root of a lot of this. Is you can have great small disturbance response behavior, and I can show a matching response to model, modeled response versus actual response, but I cannot even model momentary cessation at all, yet my resource could entirely use that for a large disturbance like a fault. And so I'll get a very large mismatch or incorrect model representation for large disturbances, but I can get a perfect model for the small disturbances. So I think that's been kind of at the root of the challenge too. So we have a lot of work to do to try to address those. And I think it's sort of been a false impression that a lot of the standards and requirements and things that are out there today will fix all of this. And I think we're seeing that they're not fixing anything really. So we need to really kind of do our due diligence to make sure that the requirements are updated and enforced, and that we follow through with making sure that those models are accurate along the way.
Okay, well, we'll expect you to have all of these things taken care of by the same time next year, Ryan. Okay,
we'll see what we can do.
Right. Here's a couple of detailed questions. One stating that the limitations of RMS simulations were touched upon, and the question, are there limitations to doing EMT simulations? I know a lot of time I hear about the EMT simulations, and people take them as really the cat's meow, that if you do an EMT simulation, then you got the absolute best correct answer. What's your view on that question? Are there limitations to doing EMT simulations? I'd like to hear from both Ryan and Bob on that.
Why don't you go first, Ryan?
And Bob, you want to go first?
Okay, I'll go. Well, it's a heavy lift. We have tools that we can do relatively detailed modeling of the entire interconnection and run dynamic studies, RMS, positive sequence domain. But when you think about that in terms of an EMT model, the scale goes up dramatically. So now we're talking about you either have to reduce the model somehow, which may or may not satisfy our inquisitiveness, or come up with new computing platforms that will facilitate this. And I think there's actually work going on in both of them. But we don't really know how we would study this stuff with the EMT model. Your thoughts, Ryan?
Yeah, I think I can just add a little bit on. I know the gentleman that asked this question quite well. I think we all do in the ESIC world. So I'll actually try to answer both of those questions that were asked. So, are there limitations to doing EMT simulations? I think yeah, there could be a false impression that the EMT, like Bob mentioned, is 100% accurate, but without some level of verification, type testing, things like that, to show that EMT model is right. Or even these real code models where I'm actually putting the actual code inside the inverter and putting that right into the model. Really, that's, kind of the ultimate goal there, is to get a representation that is nearly identical to the controls being used. And so, if there's some level of verification that the EMT model matches a type test, then how do we continue that evolution into building a very detailed model of the plant that often, the developer something may have, and then bringing that back down to an equivalence representation and proving that that's right. There's a lot of work. It is a heavy lift to do, but that's something I think we need to be headed towards. And so the next question there was, well, is EMT sort of a fallback to safeguard against not having accurate or adequate RMS positive sequence models and the parameterization of those models? I think we can't start assuming that the EMT models are going to be the ultimate solution, because there's a time and place for EMT and there's a time and place for the RMS positive sequence models. And we need to make sure that those are both an accurate, reasonable representation of what's out there. And so I think that's why these model benchmarking activities are so critical, and really verification that the model is matching the equipment, at least understanding the control settings, the tuning of the facility and all that stuff is really critical for both the EMT and the RMS positive sequence. So I'll just leave it at that for now. We do have a new task at NERC and IRPTF that's digging into the EMT modeling aspects in a lot more detail. So hopefully we'll have a lot more guidance by, say, this time next year.
Yeah,
I have just one quick thought to add. And, we're all aware that there's a lot of focus on the real-time digital simulation models. And, there's some papers I've come across that go into that in great depth, but I'm wondering if, going forward, there isn't that kind of thinking on, developing models and platforms for solutions that aren't real time, but are capable of incorporating this kind of detail. So it's kind of the same technical depth, but it doesn't have to be real time.
And I would just make the observation too that at various times in ESIG we have seen presentations which go from the actual disturbance testing of the real hardware in the field, sometimes in a test setup, a test rig setup, to the EMT simulations, to the RMS models and simulations. And you can definitely see the progression of fidelity going from RMS to the real bench. And the EMT doesn't capture everything, but someplace in between the reality and the RMS models. So a good discussion there. Ryan, a quick question here for you from ISO New England, referring to a benchmarking exercise for a wind interconnect in the ISO in 2017, and asking, should we be expecting more in the future? Will a guideline be published soon?
Yeah, thanks, Charlie. I saw that question, and I can try to provide my answer. I don't quite 100% understand the question, and so hopefully we can do some follow-up. But I think the guidance is there, right? The latest NERC IRPTF guideline that came out and was published in the planning, or approved by the planning and the operating committee, essentially says every transmission service provider should be adding into their interconnection requirements process a model benchmarking activity that verifies the EMT model and the RMS positive sequence model, and that those should have somewhat of a match. And it really should be up to the transmission entity to determine the accurateness or the reasonability of those matches and understand any lack of verification activities that take place, or lack of accuracy between those two. So, and then there's a subsequent question later down that I don't think we'll get to that I can kind of hit on the same question, it's up to the transmission entities to develop their own requirements. And I think that the transmission side is not taking that seriously in North America, right? In most of the rest of the world, there are grid codes, and those grid codes are extremely, I'll call them prescriptive. Now, other parts of the world might not call them prescriptive, but in North America, they sure are, because the NERC reliability standards and a lot of what's in the FERC process are quite vague, saying that the entities need to have their own requirements and enforce those requirements, and they need to be met by XYZ. They don't get into the level of detail on what types of controls should be used and what types of studies need to be performed and what shape of response do I have to provide. But each entity, each transmission entity per FAC 1 gets to define whatever they want for interconnecting a newly interconnecting resource to the grid or a material modification to an existing resource. So it's all of these questions on, well, what's the guidance, et cetera, are sort of coming back to that guideline we just published of it's up to the entities to develop those requirements and then go enforce those requirements. And we're, at NERC and the IRPTF, what we're trying to do is sort of vet an industry-wide recommended approach and not have it, definitely not have it become a NERC standard or anything like that. We can really sort of rely on best practices to help drive reliability through those types of interconnection requirements and things like that. And we're doing our very best to try to update the existing fleet to try to get a handle or put a tourniquet on the problems that we do have. But in the future, hopefully we have clear requirements that get enforced by local transmission service providers, and some of these issues will go away.
Okay, thanks for that. Probably have time for another question or two. So let me ask this one on black start. Do you need grid following or grid forming to do black start? And momentary cessation, part of the same question. When you want it, how do you model the cases where you want it? And when you want it to stop, how do you make that happen as well?
Well, I think, at first glance, the grid forming inverters would be capable of some black start capability within the limitations of the device, because keep in mind that black start in a lot of cases involves starting motors, and that means you have to be able to provide the inrush. So you may have limitations with regard to being able to provide that current, if in fact that's the name. But fundamentally, greater voltage and power up a device is something grid forming inverters are designed for.
So I can add some discussion that we've had in the IRPTF, if that's okay, Charlie, because I think this is a really important point, and really where we've sort of landed, and I think Bob will agree with me on this one, is that really what we need to do is specify the performance characteristics we need from resources, and then any type of resource can essentially, if they can meet those performance requirements or performance characteristics, can provide a certain service. So rather than giving it a name of grid following grid versus grid forming, even if I'm a grid forming inverter, whatever that might mean, if I don't have an energy storage or an energy device behind my inverter that's capable of providing black start capability under 24/7 operating conditions, then I'm not going to be able to meet the requirements of the grid operator to be part of a cranking path, because I need to be relied on absolutely 100% of the time if the grid goes out. So if it's the middle of the night and I don't have a large energy storage behind me, I'm not going to be able to be called a grid, a black start resource. So the controls that are programmed into the inverter itself sort of had nothing to do with that. It's what are the performance characteristics? Well, I need X amount of power for X amount of Y amount of period, and I need to be able to start with a black, a grid that's down. Well, possibly if I had, say, a battery, and I'm able to start up a set of solar panels with a battery, and then using those solar panels in, say, an isochronous mode, and then when I connect to the grid like Bob was talking about, and I synchronize to a larger grid, and I switch over to a voltage droop and a frequency droop characteristic using grid following inverters, I could maybe even provide black start services. So we're sort of looking at it backwards of saying, well, a grid forming can be black start. Well, maybe both can be black start so long as they meet a set of performance requirements the grid operator needs to define. So I think we need to look at it from that lens instead of the other way around.
Interesting observation. I'm going to skip over the momentary cessation part. I want to ask a question from Australia, since Brian, time to stay up, whatever time it is in Australia, and ask the question. Do TSOs in North America propose control settings for IBR based on outcomes of interconnection studies, or do they do studies using models provided as is and derive conclusions out of that?
I would say at present it's the latter. You agree, Ryan?
Yeah, I would say, to some respect, I was going to say unfortunately, but I'll be a little careful with my words. In most cases, the grid planner is going to receive a model from a developer or a newly interconnecting generator owner. They're going to plug that model into a base case, and if it performs correctly and nothing negative, if the grid if it meets the performance requirements and the model works functionally correct, they're going to put a stamp of approval on it. There's very little engineering that's going into saying, is this the best type of performance I can get out of that resource? And so oftentimes what we're seeing, we just talked about this in IRPTF, you're sort of getting a set of models or a set of resources that may not be supporting the grid, but they're not degrading the performance of the grid enough to the point where this is a problem, you need to make a change. And so they're getting a stamp of approval. Well, after I've connected 5 or 6 inverters with extremely fast type high gain voltage control settings, and all of a sudden things start to go unstable, I blame that last newly interconnecting resource as the problem because it didn't meet a set of performance requirements. Whereas if I had said from every resource, I'm going to try to tune you to be as be as grid friendly and supportive to the grid as possible, and as we go down the line, we could probably interconnect more resources, but we don't typically run it in that approach where I'm looking at the outcomes of the study to propose the control setting. It is, as Bob said, the other way around. We need to rethink that whole thing.
Well, I would
chicken and egg problem.
maintain that we need to look to what AEMO is doing, because they seem to be farther down this path than we are in general here.
Well, we'll just go to the ESIG activity that's going to be at the AEMO in April, and we'll be able to dig in deep in that. Okay.
That was a softball, Charlie.
We're over a little bit, but a really good discussion. A lot of questions that haven't been answered, but hopefully we'll get Ryan and Bob to give some short answers to those and what we send out. An email will go out with the presentation and the audio file and answers to any of those questions. We appreciate everybody being here on this webinar and invite you to our next one on Tuesday, January 28th at 2 p.m. That'll feature Rick O'Connell with Grid Lab and cover the topic of voltage regulation with smart inverters on the distribution system. So hope you'll be able to join us for that one. You can get information on all the webinars and meetings on our website at www.esig.energy under events, and also if you sign up for the newsletters and the informational emails. So Ryan and Bob, I want to thank you again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you next month with Rick O'Connell, or next March at the Spring Tech Workshop in Tucson. And in the meantime, take care, everyone. Thanks again for your participation, and happy holidays.
Thank you.
Thank you, Charlie.